Okay, let's get started. So today we have our 39th installment of the online Spintronics seminar series. Thank you for coming. This is Kirill Belashenko from University of Nebraska. Our speaker today is Dr. Jacob Gayles, who is a theorist, and he'll talk about hard magnetic topological semimetals in X platinum 3 harmony of Berry curvature. Dr. Gayles received his PhD in physics from Texas A&M University in 2016, where he worked in a group of Hiroshinova, and in fact, in the last couple of years, he completed his work in Germany at Johannes Gutenberg University, where he moved with Professor Sinova. And his work there was on computational and theoretical studies of chiral magnetic systems and spin-orbit torques. After that, he held a postdoctoral appointment at the Max Planck Institute for Chemical Physics of Solids in Dresden, where he worked on topological magnetic systems. And recently, he moved to Florida to join the faculty at University of South Florida in Tampa. So with this, I'll turn it over to you, Jacob. Look forward to your talk. Please go ahead.
Okay, thank you, Kirill, for the introduction and allowing me to speak at these seminar talks, which have been quite nice during these times. So the title of my talk is Hard Magnetic Topological Semimetals and the X Platinum 3 compounds, harmony of Berry curvature. In principle, I will focus on mainly these three articles here, and mostly it's focusing on the first article here. The references I will put at the top right corner throughout the talk, and I will show a page of all the references at the end. So to begin, I just actually moved here to Florida in the summer. And I am working at this building, interdisciplinary sciences building in the physics department. And my office is actually directly here. And usually it's a bit busier with students, but during these times it's quite empty. I've also just started setting up my group. And so if you would like to see the webpage, it's shown here. And also you can email me here at gayles@usf.edu. A little bit about the University of South Florida. It recently was 3 separate universities and located here, St. Petersburg, Sarasota, and Tampa. And just this year, it became one university, one accredited university altogether with 3 separate campuses. And I'm here located at the Tampa campus. And that's what this hashtag here is for, this one USF. The collaborators for this talk is primarily from my previous postdoc group, Claudia Fezer, and her group leaders, Anastasios Marco and Jan Sun. Anastasios Marco, for the experimental side, grew the films and carried out the measurements. And then also we have the group of Mazhar Ali and his PhD student, which helped in calculations. So the outline is quite simple because the talk will be actually quite simple. So quite a simple idea that we came up with for these compounds. To begin with, I will talk about the anomalous Hall effect in different regimes to refresh everyone. Secondly, I will talk about a simple model with multiple bands that we use to describe this cubic X platinum 3 compounds. And here I put cubic in quotes because due to the magnetism, you have a tetragonal symmetry, which I will explain. And lastly, I will go through the results that we see for this in a summary. So let's to start with, this is quite a common query people see, is a log-log plot of the anomalous Hall effect versus the diagonal conductivity. And what you have here is you have different regimes of the anomalous Hall effect. One is the skew scattering regime, the intrinsic, and the localized hopping regime. For different experimental materials. This we will come to get into more detail in the next slide of what the skew scattering, this different picture is. So we can break this down into the intrinsic and skew scattering into a semi-classical picture. of diffuse scattering that looks something just like a Mott scattering, where the spin of the electron is deflected by an impurity, and this impurity has a magnetic potential, so it deflects electrons with different spins in different directions. And this is usually defined in this high conductivity regime, where you have a small amount of carriers. But this actual regime, the border of this can be pushed to left or right, and you see that you have this square scaling of the anomalous Hall conductivity. And recently, in the paper, we found that when you have a Kagami lattice with a frustrated magnetism, the Dirac nature of the bands can actually supercharge these electrons to give you a very large anomalous Hall effect. And we saw some of the largest anomalous Hall effects in the skew scattering regime and this canadium, vanadium, antimony. Next, the next interesting regime is this intrinsic regime, and this is completely due to the electronic structure. So it's completely determined by the electronic structure. It happens in magnetic metals when you have a ferromagnetic magnetic order, and this order parameter gives you a deflection of the electrons when you have an external electric field that is, it gives you an extra voltage that is perpendicular. And this is completely described by what's called this Berry curvature. So this Vy is here, is just your external electric field, and this current is what you see in the presence of an electric field. And this quite well describes this regime of this mid-intrinsic, this mid-conductivity regime where you have not so high but not so low conductivities. You also have this localized Hopman regime, which is a bit more complicated, and it's a mixture of also this intrinsic skew scattering, also with this last term called the side jump, where you get an extra phase shift to your spins with any impurity. However, this term is independent of the number of impurity scatterers. You can classify these into two groups. So the conductivity, you can separate into one term called beta and one term, or B and A. A is has some dependence. And the original way was linear. Now people see more, it can actually be a square dependence, which is what we found for the Canadian potassium, vanadium, antimony. And then you have the intrinsic and side jump terms, which are independent of the longitudinal scattering. And this you can see very clearly in the intrinsic regime, where you have this this flat plateau of all the materials. So now we talked about this intrinsic, so we're going to focus mostly on this intrinsic for the rest of the talk. We want to show some simple models of what gives rise to this anomalous Hall effect, and this is usually when you have some band inversion with spin-over coupling and an external magnetic field, an internal magnetic field from some magnetization. And so for two simple bands, this gives you anomalous Hall effect, and once you change the chirality or inverse the magnetization, you can inverse the anomalous Hall conductivity. And this is quite known, when we'll go through this more. Another case you can do is that you can bring a four-band model to this. And what happens here is if they have opposite chirality or opposite magnetization, then the anomalous Hall effect will essentially cancel. And this is actually quite evident in a lot of materials. I will only show one in this talk today. And lastly is that this new case that we want to discuss is where you have two bands, four sets of bands that are work together, where you get this harmony to actually enhance the Berry curvature, which strangely has not been seen quite widely in experiments in theory. So the simple model, is has actually worked quite well. So you have things like these Wells semimetals, cobalt 310 sulfur, which has these two wild points, and this shows quite a high maximum of the anomalous Hall effect of about 1200 Siemens per centimeter. And this is nice because that's a very simple band structure. And what's nice about this Wells semimetal is before spin-over coupling, you have this nodal line, and once you add spin-over coupling, this nodal line is gapped across space, except for at these wild points, which makes this what people can say as a true true semi-metal. And the fact that you have this continuous gapping across your Fermi energy, except at these wild points. Other materials such that have been found similar to this is this Co2MnGa gallium, which also shows very large transport in respect to the thermal kernel parts of the anomalous Hall effect. And then it's also been recently predicted that as you take these three-dimensional materials down to the 2D limit, that you can gap these wild points and even create a quantum anomalous Hall effect of these materials. Now, in the other model, what we have is something, this is the material cobalt titanium tin, which is very similar to the Co2MnGa gallium, but here, the cobalt and titanium they show this cancel out behavior, and you get a very small anomalous Hall effect. And here is to show the band structure that has wild points above the Fermi energy and the anomalous Hall effect, and the Berry curvature to distribute it in the Munter space, which has both positive and negative contributions. So we can actually reproduce the top two band structures with a simple Hamiltonian for a wild Hamiltonian, where we have some spin orbit term, a hopping term, and the magnetization term. And by either flipping the magnetization term, we can go between, sorry, the first and second band inversions. And by changing the chirality here, we can also go between these two. To enhance the Berry curvature, you have to actually switch both the chirality and the magnetization here. And you can just create another Hamiltonian here to add to this with a coupling term to actually create this enhancement term. So now let's go to the cubic X platinum 3 compound. So structurally, these compounds are cubic. On the corners are a main 3D element group, and on the faces you have platinum. And once you add magnetism, what happens is the side faces are distinguished from the top faces depending on the direction of the magnetism. And here what we did is we carried out some DFT calculations to calculate the total magnetic moment, shown in black, which just shows the increase as a function of chromium into vanadium and chromium into manganese. Whereas we also calculate the orbital moment and the moment of the platinum. And here, the moment of the platinum, you see actually changes sign, which becomes important for the mixing of these Berry curvature and bands. And for the experimental part, what we did is we grew these chromium platinum materials. Here we distinguished the two different films of chromium by these indices, which are not completely accurate because there's about a 2% error in the EDX measurements of these films, but we grew them on top of aluminum oxide, MgO, and capped it with aluminum oxide. And it's about 60 nanometers thick. And what we did is we grew it so that the normal to the 111 is out of plane, so that the three lattice vectors have an equal strain on them, so it keeps the cubic nature. And we calculated the magnetism for this, and we found that it has this hysteresis loop. So the black shows the in-plane magnetization, and the color shows the outer plane magnetization at different temperatures. It also shows this hysteresis loop and this hard magnetic phase going from the in-plane to outer plane direction, which is quite different for a cubic system. As we continue more of the experimental properties, we also calculate for completeness things like the longitudinal resistivity, and we find triple R ratios of 1.7 and 0.8 for the two materials. sorry. To continue on, we have the magnetic resistance for the outer plane direction, and also for the in plane direction, which is dramatically increased when the magnetic field is placed in plane compared to the outer plane direction. So now let's get back to the theory, specifically these X platinum compounds, and we focus here mostly on the chromium platinum 3 because it shows the most interesting effects of the 3 compounds listed above. And what we find is that we actually have 2 sets of bands that contribute to this anomalous Hall effect. And the first set is shown here in orange, and the second set in blue. And these are actually topologically disconnected. And what we can do is, well, for one, we calculate the Kubel formula, which is shown here as a function of Fermi energy. And we also calculate what's called this hyperbolicity factor of this material. And the hyperbolicity, what it does is it takes points on the Fermi surface and it calculates the trajectory of these points. It's a new type of way that we were developing to actually calculate the anomalous Hall effect and transport properties. And it calculates the trajectory of these points on the Fermi surface. Similar to how this cat, when this cat is moving on a geodesic surface, it will follow the path of the surface as described here. Particularly, we like this approach because it has a very good correlation with experiment. Above, you see a list of materials, popular materials: cobalt, iron, manganese 3 germanium, compared to this hyperbolicity factor, which almost shows a 1-to-1 correlation. Whereas when we compare with the anomalous Hall effect in the Kubel, this correlation deviates. We believe here this hyperbolicity function sorry, actually captures more of the physics than the Kubel in this case. So back to the band structures, we come back to this cobalt 310, sulfur 2, and here is a quite simple band structure. You can see here we show the majority versus the minority with spin orbit coupling. And here, once adding spin orbit, you can see the gaps open here, but it's not a drastic change in the band structure from the magnetic to the magnetic with no spin orbit coupling to the case with spin orbit coupling. And here we also show for the cobalt manganese to gallium, which also shows these gapping of the wild points. And also, it's not a drastic change here. Whereas the chromium platinum 3 actually has quite a drastic change due to the spin orbit of the platinum. And this is also causes this large orbital moment that you see in the system. We can continue and actually look at these 2 sets of bands for the different systems. So if we take here at the vanadium platinum 3, we can calculate the anomalous Hall effect due to these bands, which shows a little bit of reciprocity. And here in the black is the total, the red is from the red set of band, the blue from the blue, and the dashed black here is from all of the bands below and above these materials, below and above these 2 sets of bands. And here you see primarily the anomalous Hall effect is due from these 2 sets of bands using this Kubel formula technique. Further on, we can also see this is also enhanced in the chromium platinum when these bands are closer together and they have more overlap. And lastly, in the manganese platinum 3, when these bands become nearly on top of each other, the result is reduced more. So yeah, again, here I just show the magnetization, and I compare the anomalous Hall effect as a function of the chromium content in vanadium and manganese, and also the anomalous Nernst effect here, which is the thermal counterpart of the anomalous Hall effect. Furthermore, we do some analysis of the bands, the two sets of bands we were looking at, the red and blue. And here we just take the in this case we have the cubic 100 plane, and we look at the difference between the two bands. And for the non-spin-orbit case, where we have this degenerate nodal line in red here, and also this is on the 110 phase. Upon anti-spin-orbit coupling, we generate this Berry curvature, which is shown here for the three-dimensional case. And these are the two planes shown here, where these degenerate nodal lines actually have a strong change in distribution from the non-SOC case to the SOC case, the spin-orbit case. And this is just the Berry curvature of those two sets of bands shown here. And this here is for all bands up to the Fermi energy. Further on, we measured the anomalous Hall effect of these materials in the experiments. So this is here just the anomalous Hall effect as a function of the field, which shows the same hysteresis that you had for the outer plane material at different temperatures. And what we can do is we can separate the side jump and skew scattering, the side jump plus intrinsic from the skew scattering. And for the two different samples, we actually get quite different skew scatterings, which suggests that one of the samples has more impurities and the growth is a bit different here. What's nice is here we get this final plot, which I show on the end, which shows the, again, that Hall effect versus the longitudinal conductivity, sigma XX, the anomalous Hall effect. And here we just focus on intrinsic materials. And so here is also only films that we're looking at. So what we have here in the orange is the cobalt-310, we have the cobalt-2 gallium, and we also have the iron, gadolinium, and nickel cobalt elemental materials. I go to the next slide, which is just this slide here, this picture, just so it's enlarged. And so focusing on this, we also see some interesting features here. One is these chromium platinum materials have a very excellent agreement with the theoretical values as compared to the cobalt-310, which also does not match up to for the films, the theoretical value where the single crystals do. And this is actually something quite common for these topological materials, is that they are not matched very well with the theoretical values from the films. And this may just be due to sample preparation and impurities in the system. However, with this chromium platinum, as I showed before, we do have these impurities in there, and you get a very robust anomalous Hall effect from this. Furthermore, what you can see is that you can distinguish these different materials from this graph. So on the right, you have these elemental metals, which show pretty much a flat and constant anomalous Hall effect, which is this intrinsic effect. And then once they start to get to high conductivities, they become skew scattering materials, and the skew scattering starts to dominate the anomalous Hall effect. And then on the left, what you have is these topological materials, which are cobalt-310 and cobalt-2 gallium. And the cobalt-2 gallium and cobalt-310, they have a very low conductivity, and this is due to this wild semi-metal dispersion, where you have a very low density of states to this electronic band structure. And interestingly here, what you see for the chromium platinum is that it exists directly in the middle of these two bands. And if you remember from the band structure, you saw that we had these topological bands, but we also had other bands that interacted there at the Fermi level. So it's kind of a mixture between these two materials. So in summary, we discussed this cubic compound, this chromium platinum 3, which gets distorted from the magnetic symmetry group to be tetragonal, and shows this enhancement of the Berry curvature for the anomalous Hall effect, which is clearly shown from the experiment and in theory. Sorry, just to remind you guys, I'm here at the University of South Florida, and I would like to thank you for your attention. Here are the references for the work.
Thank you very much, Jacob, for this interesting talk. So we are happy to take questions. So if in Zoom, please use the raise hand feature, and I'll call upon you. If you're watching on Twitch, you can type a question in the chat box, and I'll read it for you. So any questions in Zoom, please? Yes, Matthias, please go ahead.
Hey, Jacob, thanks a lot for this nice talk. I have a question concerning these like chromium, platinum 3 materials. What are the other magnetic properties, like typical switching fields in like thin films? I'm just trying to understand if these are materials that I can access with my typical techniques. Are these like high anisotropy or low anisotropy materials?
So I would say they're mid anisotropy. So they're not. They have hard magnetic properties, but they're not completely hard magnetic. One of the reasons that it's on archive, because we wanted to get the work out there quickly, but we're still having trouble getting correctly the transition temperature, which we believe to be around 600 or 700. If we go back, it's actually quite complicated to measure the difference between these two magnetic moments. I think that they're quite well-known materials, so they've been around in the 80s. They're used for magneto-optical recording devices because they have a very large magneto-Curry effect, which is just the AC equivalent of the anomalous Hall effect. But the actual switching field, I think that also depends a lot on the sample growth and the thickness of the film and things like this.
So if they've been used for optical recording, then I guess there's enough literature out there so I can have a look.
Yeah.
Okay.
There's also and the references. I list the major articles, and I think.
So which is a good article as an introduction to the magnetic properties of these materials?
I just like Oppener, so that's personally me.
He's a really good theoretician.
Yeah, that's personally me, but depends on who you are.
Okay. Yeah, great. Thanks. I'll have a look. Cheers.
So he also gives a nice review and things of these things. Yeah.
Okay, great.
Okay, Stefan, please go ahead.
Hi, Jacob. Was nice seeing you and was nice hearing your talk. I really enjoyed it. I have two questions. Some of the materials was made by your colleague, and I think you referred to them as films. Do you see any thickness dependence on the anomalous Hall?
I think that is the next attempt to go to. Is actually what they're doing now is to grow the thickness dependence. Mm-hmm. I would suspect not greatly. I mean, comparatively for the Co2Mnganese gallium, we see a very large thickness dependence for the anomalous Hall. But this seems already at 60 nanometers to be quite sufficient to reproduce the theory.
Mm-hmm. I have another point. If I remember correctly, if you continue in the periodic table, iron becomes antiferromagnetic.
Iron platinum 3. Yes, I believe so, yeah.
Did you look at them? What happens there?
Theoretically, no, I have not looked at them. I don't know if
because you had this idea, because you alluded to this idea that you need this harmony in the bands to get the effects strong. And of course, if you have a ferromagnetic state, you have easily a spin up and a spin down state following in parallel. And so the effect could be small. But if you have an antiferromagnetic state, maybe you have an inversion, and maybe you have two states, what you call the majority states, and two of the minority states. And so it could be different.
Yeah, I mean, for the thing, I think the anomalous Hall effect would be 0 because you don't have these symmetries from this crystal Hall for the crystal Hall effect. But for spin Hall effects, it may also be interesting. In this case, I believe.
Okay.
Did it answer your question?
No, I was wondering whether you looked at them and tried to do something in this direction.
Yes, I have not tried to iron platinum 3 yet. No.
Okay, thank you. Vivek, you're next.
Hey, Jacob. Yeah, I just wanted to ask you a question about the theoretical methods you're using. So you mentioned that you were using the Kubo formula, but then you introduced something else. I don't remember what the name was. And you showed a picture of the cat and the geodesics and all that stuff.
Yeah.
Can you tell me a little bit more about what that method is and what sort of does it add, relative to the Kubo formula in terms of what it's calculating?
So I think, me and Vivek also were PhD students together, but I think we, for the terms of the Kubo formula, a lot of problems with the Kubo formula is that it's very hard around these irregular topological points to calculate. So you need an adaptive mesh to do it, or you need many, many, many K points. Because it's the problem is that each point that you calculate the barrier curvature at is independent. So you need to have many points to actually reproduce things accurately. And so what we're doing here is that we're just taking the Fermi surface, whatever it looks like, we don't know what it looks like, and we throw it in and we say, how can you move on this Fermi surface to give you points that would, so we map the Fermi surface, each point on the Fermi surface, but it's also connected to the points around it. So do you have an elliptic point? Do you have a spherical point? Do you have a hyperbolic point? And things that are hyperbolic would give rise to things that are like anomalous Hall effect in behavior.
So is it kind of more of an efficient way of essentially?
It's very efficient. Because also we don't have to use any interpolated band structures. So we can just take the pure self-consistent calculation and measure that out, take this out. There's still some things we need to work through, but it's quite efficient in the sense. So I think we converge things already at like 30 K points per direction.
Okay, cool, thanks.
There's an archive paper on there which we put sorry.
Okay, cool.
Yeah, it just happened. We chose this just because it happened that the chromium platinum came out very nicely for this to explain it. Because but I think in Kubo I would have never came to this conclusion. But
cool. All right.
Okay, thank you. Axel, your next question, please.
Hey, nice talk. I was wondering, since you did make the comparison to the experimental films and you did mention that they were strained. Now your calculations are, I'm sure, for the unstrained case. So I'm wondering what the strain may do and how things may also modify if you go on a different orientation of the MGO, so where you got, don't maintain the cubic symmetry.
So yeah, we kind of had some, because we were in Claudia's group, of course, at the films group, Claudia group, we had some, a priori, we had some knowledge of that the strain can change the if it's a cubic system, it can make it tetragonal. So we tried to grow it so that the three crystal axes are growing out. So there is strain, but it's equal on all crystal axes. So the 111 orientation is out of the plane, yeah. So there's no strain in this case. The strain, I believe, would not change it drastically. Surprisingly, for this system, there's not a lot of, I didn't put it in the supplementary, but there's not a lot of anisotropy for different directions of the anomalous Hall effect. So from there, I would say the strain would not change it drastically either. It is very anisotropic in the magnetization. So going from, for a cubic material, going from the 111 to the 100, which is also relevant in the theoretical calculations, I get something on the order of a milli eV. But the anomalous Hall effect is the transport is not very anisotropic.
All right, thanks.
Thank you. Shin, please go ahead.
Thank you, Jacob, for the very interesting talk. So just on this slide, the chromium platinum sample has a much higher anomalous Hall conductivity than the chromium manganese gallium film, and I suppose this is mostly coming from the large spin orbit coupling from platinum. Is it?
No, I wouldn't say it's I wouldn't say it's a large spin orbit coupling of platinum. Just from my understanding of things, because gadolinium has a very large spin orbit coupling, but it's not drastically larger than iron. And I think this that is an important feature. I think that's been coming in the last decade or so, is that it's not only the spin over coupling and things like this, but it's also the ingredients at the Fermi surface. Yeah.
Right.
I mean, this is for the spin Hall effect, right? You have for platinum, you have the largest, but if you go higher in spin over coupling, it doesn't increase your spin Hall effect.
Right. So, but if you have you calculated the spin Hall effect rather than the anomalous Hall effect, or the spin anomalous Hall effect?
The spin anomalous Hall effect. So the spin Hall effect on a magnetic material, you mean?
Yes. So if I want to use this particular material as a spin current source,
I have not calculated the spin Hall effect. I could possibly do that though.
but it's the same Kubo formula, right? It's just kind of
It's a little bit different though. I mean, you have a commutator with the spin, right? So
okay, yeah.
It's not exactly the same, right? So the anomalous Hall effect would be the addition of the charges. The spin Hall effect would be the subtraction of the spins, right?
Mm-hmm.
Yeah.
Thank you.
Yeah. So, but it's interesting, I think. Yeah.
Yeah, I'm interested in anything that's magnetic as a spin current source. So that's why I'm asking. Thank you.
Okay, thank you. So if you have a question, please use the raise hand feature. It should be under the participants panel. If you don't see that, you can send me a private chat message. Let me ask you something. You showed in one of the earlier slides in the talk a plot showing the like for multiple materials, the dependence of the Hall effect and the conductivity when you discussed how
this one.
Yeah. So you mentioned that so you have some materials that seem to have the exponent of 2 in the skew scattering regime, this sigma xx squared. Do you have a tentative explanation why they behave this way?
Yeah, this is, I mean, it's not completely clear, I think, but if this is, I mean, this first one you see those two is from Tian, which said, I think this PRL from Tian that says you can rescale this these iron films actually is 2. It's not linear here. And so this comes, I mean, you also have this phonon contributions that have a contribution to this scattering part, but it is I think it's not very, very clear of why it's exactly 2. But I think you can say for sure that it's, I mean, it's a log plot, right? So you always, there's definitely not a 1. I mean, this is just iron, and this is directly from the anomalous Hall effect review.
Mm-hmm.
So I'm not exactly sure how this linear scaling came about ever, but I don't think there's any material. I don't know of any material that actually shows a linear scaling properly instead of a square law.
Yeah. So another question that I ask everybody who calculates intrinsic effects from the Berry curvature. So the intrinsic effect supposedly works in this relatively dirty regime where you have the resistivity of 10 to 100 micron centimeters.
Mm-hmm.
So if you look at the disorder broadened band structure, so typically I think you would see that the broadening of the bands would be of the same order as the gaps that generate the Berry curvature. So is there a good reason to expect that what we see is really Berry curvature related and doesn't come from vertex corrections and or something considerably modified by disorder?
Yeah, I think that's a very relevant question. I think that is a system to system, depends on the size of the gap. Yes, when the gap is too small, you have to kind of throw out this Kubo type approach. Yeah, if your broadening is larger than the gap, then you're destroying all the information there, right?
Yes. So what comes to mind is this, one of the first calculations of the spin Hall effect in platinum from first principles, which showed that if you use Fermi broadening, you see that the spin Hall conductivity is decreased by a factor of 10 when you get to room temperature.
Mm-hmm.
And it is clear that typical disorder at room temperature is much larger than 300 Kelvin.
Mm-hmm.
So in this case, it's natural to question that it's the Berry curvature that generates this effect.
The anomalous Hall effect, you mean?
Well, in that case, it's the spin Hall, but it's the same kind of argument. Yeah, I'm not sure. I mean, there is no anomalous Hall effect in platinum, but the same question about the relation between the gaps that generate the Berry curvature and the contributions to these intrinsic effects and the scale of the disorder broadening. So it doesn't seem like disorder broadening is much smaller than those gaps.
Yeah, but also, I mean, in the way we're calculating this broadening is not very realistic. Also, yeah. So this broadening is taken into everything into account. I mean, it's just smearing the bands, yeah. And
Yeah, but when you calculate
that is not the real
curvature,
temperature
doesn't
effect of
matter.
experiment, right?
When you calculate the Berry curvature, you don't need broadening, really. You just assume small because it doesn't depend on it in that limit.
Yes, I mean you do need some amount of broadening. If you make it 0, then
sure,
in some cases it's gonna you get an ill-defined answer, right?
Well, yeah, but
I mean, essentially, I mean, it also depends on how people calculate it, right? I mean, so if you're doing a pure numerical calculation, you should converge it, right? So you should always decrease your broadening until things are constant.
Well, sure.
And so, I mean,
but that's my point.
If your broadening is larger than the gap, then you'll have, as soon as you go into the gap for your broadening, then your Berry curvature will not be constant anymore, right? Yeah.
Well, precisely.
As you go into the gap, once you're in the gap, it's constant, yeah.
But the question is, when you calculate it, you assume the limit that the broadening goes to 0. Mm-hmm. But experimentally, you then compare to a dirty limit where it's actually large and large enough that the skew scattering is suppressed. But if you start looking at the broadening in that regime, it's not small compared to the band gaps. I mean, to these anti-crossing.
The broadening from, so you're saying you take this point, this broadening is not small compared to the band gap.
Yeah. If you look at disorder broadening that you need, that you will obtain in a material with this conductivity, mm-hmm. It's not going to be small.
Yeah, it's not going to be small, but you also have, like, I mean, your crystals, your actual experiment is not going to be a pure sample, yeah?
Right.
So, I mean, you're saying, okay, we're saying, I mean, because this here, we can say, okay, yeah, this becomes a very clean crystal in this regime, yeah? Mm-hmm. And there, I mean, it's clear that the skew scattering will dominate, but you can never get rid of all the impurities, right? So it's always going to be the skew scattering that dominates.
Yeah.
But once you come here, I mean, because I mean, effectively what you're doing is, usually what you're doing here, you're just changing the temperature, right? To change this longitudinal resistivity.
Right. Or you have samples of different quality.
Yeah, or you have samples of different quality. But I mean, so this measurement and this measurement, so these are all just changing the temperature, but these are different samples here. And this here is just changing the temperature. And so what you really want to, what we're looking at here is this effect as you go to this 0 temperature. Yeah. So we're not looking at this point in particular, but we're looking at the collection of points when it's flat. Mm-hmm. And so that's also the point I was trying to make with the chromium platinum, is that this actually gets to this point where it's what we call intrinsic. So it doesn't depend on the scattering, but you also always have side jump in these. So this is
yeah. That's
it's not as simple to just say yes. It's purely intrinsic. Yeah.
Yeah. Okay.
So to some part, yes, I agree with you. I mean, you can't just purely say it's intrinsic.
Right. Okay. Thank you. Any other questions, please? Questions or comments? Let me check Twitch. Okay, looks like no further questions. So let's thank Jacob again for this nice talk.